So for rules of exponents for power to a power, so it's our next rule or law, depending on where you see it. But I like to call it distribution. So if raising a power to a power, multiply the exponents. So distribute in to the exponent to exponent. And that is more important when there's more than one term, which is power of the product. But if you make that your general rule across the board, it should always work. So that's x squared, then raise to the 8 power. Your parentheses is what lets you know. So then this is going to be x. And what that means is you did x times x, x times x, and you're going to do it 8 times. So 2 times 8, we should know, is 16. So that's 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So that's 16 x's. So x to the 16 power is your final answer. So obviously you don't have to write those out, but that's what that 8 is doing on the outside. It's saying write x squared, which is x times x, 8 times, and then how many x's are there? So in this case, y to the negative 3 raised to the negative 4. Normally we're going to see those negatives and be like, oh, whoa, hold on. But first, you want to actually simplify. You want to actually do that multiplication because we know a negative 3 times a negative 4 is going to give me a positive 12. So it's going to be y to the positive 12th power. So power of a product, so that means there's multiplication going on the inside. This is where yesterday I mentioned putting those imaginary ones, and then you're still doing the distribution game as soon as you put that imaginary one. Everything on the inside gets that exponent if there's a parentheses there. So this 3, if I put a 1, and a 1, so that's 4, 1. I'm just making sure it's big enough for you to see. Y1, Z1, all to the 3rd power. So you're going to distribute that through to everyone. So that is going to be 4 to the 3rd power, which we can solve that. So we're going to simplify that in a little bit. 3 to the 3rd power, x third to the 3rd power. So that's 3 times 3 is x to the 9th. Then 3 times 1, which is going to be y to the 3rd. And then 3 times 1, which will be z to the 3rd. Now, the 9, the 3 are perfect on the variables, but that 4 to the 3rd power means 4 times 4 times 4, which is something you can get a very nice whole number. So we're going to go ahead and simplify that. So the answer is going to be 64, x to the 9th power, y to the 3rd power, z to the 3rd power, and now you're finished. So for our next guy, this is a negative 2, so we're going to put imaginary 1, imaginary 1. So negative 2 times 1, that's going to be 7 to the negative 2. Negative 2 times 1, x to the negative 2. Negative 2 times the negative 2 is going to give me y to the positive 4. That y4 is perfect. These x negative 2's, though, are going to pose us a problem. Yesterday I showed you where we could put that imaginary 1 underneath. So when it is a negative exponent, you're going to drop it down into the denominator. It's going to become the reciprocal and become positive. So that means I now have y to the 4th power over 7 squared times x squared. And we do know that 7 squared is a nice number, so y to the 4th power still on the top, 49x squared. And that's your final answer for that guy. So again, I'll put a 1 if there isn't an exponent, just so you don't accidentally forget. So negative 2 times 1, so that's 6 to the negative 2. Negative 2 times a negative 6 is x12. Negative 2 times negative 7 is y14. Negative 2 times 0, anything times 0 is 0, so that's still going to be z to the 0 power. Anything to the power of none is 1, so it just goes away. Our negative is a problem. The positives, those are not a problem. So we're going to have x12, x to the 14th, all over 6 squared, which can be simplified to x to the 12th, y to the 14th. Sorry, I drew an x. I did x twice over there. I just saw it. So that's our y. And then 6 times 6 is 36. So again, there's imaginary ones. So in my mind, I don't leave anybody else. So if there's not an exponent, whether it be a whole number or a variable, put imaginary 1. So that way, if it's on the outside of the parentheses, it makes it all the way through. Power of a quotient is no different than power of a product, except that's on the inside is division versus multiplication. You still are going to put those ones there, and everybody's going to get it. So that's going to be 3 squared over 5 squared, which we can simplify or expand. 3 times 3 is 9, and 5 times 5 is 25. So that's our answer for that guy. We're going to put imaginary 1 here. So 2 squared, a to the 10th, b to the 14th. Because 2 times 5 is 10, 2 times 1 is 2, and that's what these guys are. And then 2 times 7 is 14. 2 squared can be solved. So we'll do a to the 10th power with a 4 in front of it and b 14 as our final answer. 1, so 3 to the 1. So 3 times 1 is 3, so 3 cubed. 3 times the negative 4 is going to be a to the negative 12. 3 times 7 is b to the 21. So we have a to the negative 12 is a problem and has to go to the basement. And 3 to the 3rd power is 3 times 3 times 3. So 3 times 3 is 9 times 3 is 27. So 27, b 21, a positive 12. Because once it switches, it becomes reciprocal or drops like it's hot or raise the roof, as I said in live class. It does become positive. So that's our final answer for that one. And these all have exponents. So negative 6 times a negative 2 is a to the 12th. Negative 6 times a negative 5 is b 30. Negative 6 times negative 11 is c 66. None of these can be reduced because they all have different bases. So at that point, you're done. And all your negatives took care of itself. So no worries there. All right, guys. Hopefully that makes sense. If you have any more questions, definitely check out the extra help. And good luck at Delta today.